it's not clear whether, certainly not going to talk about numbers here. But I am going to talk about L functions, various kinds, and what is the purpose of talking about L functions. So in the middle is L functions. Now in one direction towards the left there are two arrows. The really pertinent arrow is a solid arrow. And the idea is that once one knows something about L functions, one can, on the basis either of conjectures or theorems, extract Diophantine information of various kinds. For example, there are various conjectures known as state conjectures, first and iris. These are some very, very special cases, but they all say that if one knows something about an L function, about some kind of function of a complex variable that has poles of a certain kind, that it has certain values, then you can get some concrete information about Diophantine problems. Apart from the difficulty of constructing, of proving the theorems that are implicit in that arrow, there's the problem of dealing with the L functions themselves, and that's what we want to concentrate on now. And the only way that's known,
Where did you get a unique card?
It's not worthwhile. I bet you on that. Yeah. All right. So, the only way known for extracting information about the analytic behavior of the pertinent L functions is to connect them with automorphic forms. So the solid information here, apart from whatever you may see in various papers, the really pertinent information says automorphic form goes to L function. And we want to see today what kind of L functions we're considering, and not so much, and what we want to see today, or examine today rather, are the consequences of the existence even of this proposed connection, of the truth of the statement that any L function that arises from a Diophantine problem actually is also an L function that arises from automorphic forms and therefore can be handled. L functions, some L functions at least that arise from automorphic forms, can be handled by standard technique of Fourier analysis. Let me just get rid of this. Something else has happened. Battery back.
Yeah, just put that switch off, then the screen will go off.
Where do I put this now? Up higher? No. All right. Let's hope for the best.
That would be other way up.
If we've had so many technical delays, let me just take another minute to take care of these things. All right. So the first thing to know is what we're dealing. What are these L functions that we're dealing with? So as I said, well, let me remind you, of course, what the classical paradigm is for this connection. The classical paradigm is of course ordinary class field theory, which now this used to be regarded as an extremely obscure subject, especially when I was a graduate student. It was something that no one was expected to know anything about, and now it's something that everyone is supposed to know, but never is supposed to mention explicitly or deal with in any concrete way. But here, of course, the L functions that appear in the middle, especially are Dirichlet L functions. So functions basically of the following form: summation from n equal 1 to infinity, chi of n over n to the s, where n is chi is some periodic function of n. And so it's something that, because chi is a periodic function, these things can be handled by Fourier analysis. And what occurs over here, the Diophantine problems, are zero-dimensional Diophantine problems. So a zero-dimensional Diophantine problem is basically a problem defined by solving an equation f of x equals 0, where f is a polynomial in a single variable. F of x is equal to x to the n plus a1 x to the n minus 1 plus a2 x to the n minus 2, and so on. And there are various things that you might want to say about the solutions of this equation that, of course, won't be in general rational numbers, even if a1, a2, and so on, as we suppose are rational, but that will be algebraic numbers. And of course, I mean, this is just for those who don't know what class field theory is. One has to specialize even more than that. One has to specialize to the case, say, that the Galois group of this equation is abelian. That's somehow to give you an idea of how primitive the theory of Diophantine equations is, that one can only, from the point of view of L functions, that even this very simple case is extremely arcane and difficult. It took about 100 years to develop. And here, the connection here with L functions, here, as I just explained, is really a connection with Fourier analysis on the line. So, R. And that's I'm not going to go into it, but that's the classical situation. So, let's just try to see in general how one associates an L function to Diophantine problems. So, it's useful to consider not just an arbitrary number field, not just the rational numbers, but any finite number field over Q. So finite dimensional number field, finite dimensional over Q. And how does one construct the L functions? Well, one starts off with some representation of the Galois group the Galois group of f bar over f. Now, think of this as a finite dimensional complex representation, finite dimensional complex representation, and that corresponds to Artin L functions, but in fact, in the context of a highly developed theory, so in the context of, say, L-adic cohomology theory, this can be an L-adic representation, but for the structural purposes, one doesn't need to know that. This case is certainly hard enough, as this suggests, for our present purposes. This suggests that already the case that this representation is a one-dimensional complex representation is difficult. Now, this L function has the following form. It will be the product over all the prime ideals, or all but a finite collection of prime ideals. So this L function has the following form. For all practical purposes, it's a function of a complex variable S. It's given as a product. And what are the individual terms in this product? They are of the form product from j equal 1 up to n. So n is a fixed number. N would be, we call the degree of the L function. And then we'd have numbers here, 1 minus alpha j of p. So they depend upon the prime. And then over the norm of p to the power s. So you should take, at any moment, if you're not particularly used to thinking in terms of number fields, take f equal to q, and then this p becomes an ordinary prime p, and the norm of p becomes p itself. So a typical case here would be, for L of s, would be the zeta function of s, which is product over all p of 1 over 1 minus 1 over p to the s. So in that case, all these numbers alpha j of p are equal to 1, n is equal to 1, and we don't have to exclude any finite set of primes. For more general Dirichlet L functions, where key was a more complicated periodic function and not the constant 1, the alpha j's would depend upon p. So this is a case of degree 1. So n, the degree is equal to 1. So, but how do we get, so that's the typical structure of an L function. So it's a product over almost all but finitely many primes, 1 over 1 minus a constant divided by the norm of p of power s, and the number of these terms is a fixed number, integer independent of p. So the question becomes, say, for these, what we could call Diophantine L functions, those associated to Diophantine problems, how do we obtain these numbers? Well, here's the one thing that we have to know, that we have to take, say, from Frobenius, we have to take the fact that for every prime p, we can associate an element, the Frobenius element, which is really a conjugacy class. So this is a Frobenius element in the Galois group of f bar over f. And all we do, once we have this representation, finite dimensional complex representation, and it's that to which we're going to attach the L function. So it would be L of s, we attach to rho, we take the product over p, and then we take 1 over the determinant of 1 minus rho of this Frobenius element divided by the norm of p to the s. So in other words, the numbers alpha 1 up to alpha p, alpha n of p, are just the eigenvalues of this matrix rho of phi of p. Now, in fact, I can't define, there are a finite set of places in which this element is not defined, so I just exclude those. So n, the degree of the L function, is the degree of the representation. And how we get from a Diophantine problem by means of the L-adic cohomology theory to a representation is unimportant here. What we need to stress is the structure, the basic structure of the L function. So that's one side of, in general, that's one side of the picture. Those are the L functions that come from here, and about which we need to know something, and about which we usually don't know anything to begin with. For example, a typical example would be the following. Typical example, or the simplest example, would be the following. If I won't define rho, but let me tell you how I built this. I could say, take f equal q, take a quadratic extension of f, say defined by an equation x squared minus p equals 0, and no, x squared minus, so some number a equals 0, a rational number. And then what I could say is this number was equal to be, this number, n would be 1, and I could say this number would be plus or minus 1 according to whether the corresponding congruence was solvable modulo the prime p. So this would be p equal p. That's not very well expressed. But I just wanted to give you one simple example of such an equation, and for which n is equal to 1, and where the Diophantine equation implicit in alpha j of p is whether or not the equation x squared minus a congruent to 0 has a solution modulo the prime p. Now, on the other hand, so that would be a Diophantine L function. What about the automorphic L functions, which are to serve as a basis of comparison, for which the L functions, the automorphic L functions that are to serve as a basis for comparison will be defined in general in a different way, and in particular, in this particular case, they'd be defined in a different way because they would say define alpha j of p, which is just alpha 1, prime p, by somehow or other by the remainder of p upon division by some number, upon division by delta, where delta was some number that depended upon a. That would be the typical deficit. That would be a concrete case. In general, an automorphic L function has the same form. It has the same form as these Diophantine L functions, namely, it's the product over primes. I exclude for some reason or other a finite set, and then I have 1 over 1 minus beta 1 of p over norm of p to the s, all the way down to 1 minus 1 over beta n of p over norm of p to the s. So once again, it's defined by the same kind of product. So for each of finitely many primes, I have to give n numbers. And the question is, how do I determine those n numbers? So one way I determine them from a representation in the Frobenius element. Now I have to determine them in an altogether different way, a way which is ultimately more elementary, but which is at first sight much more complicated. All right, and what is that? Well, that means I have to begin with what is called an automorphic representation. And let's take an automorphic representation for the moment as something undefined, as a black box, and let's look at it structurally. And let's take, in order that you don't have to continually look at my rather ill-formed Gothic P's, let's take F to be Q. So this automorphic representation I'll call pi. Now, what is this? It's really a representation of GL, and this number n here will be GLn. Then I have to put the adels of Q, but let's not worry for the moment what the adels of Q are. All I want to stress now is that this pi is related to some representation of GLn, and in particular associated to this pi is for every prime p a representation pi p. Now it's a representation of GLn QP. This is a big group. This is a locally compact topological group, and this pi will be an irreducible representation, and usually it will be infinite dimensional. It will also usually be unitary, but that's beside the point. But it is a big representation. That's, in some sense, unfortunate, because in spite of the fact that pi p is a very large representation, it contains very little, in itself, very little information. You see, usually, and this will be true, if I start from pi, then for all p outside of some finite set of s, pi p will contain the trivial representation of the following group of GLn, not of QP of course, but of the integers in QP, namely ZP. So this is the group of n by n matrices whose entries are integral as far as as elements of this local field, QP, and whose determinant is also an integral and invertible as an integral element, so that these things have inverses in the same set. So pi will contain the trivial representation of, that's a fact. That's a fact one needs to know from representation theory. Or, just that for almost all p, pi p will contain that. And it will contain it with multiplicity 1. That means that there's a unique basically unique V up to scalars, unique up to scalars, such that pi sub k, pi p of kv is equal to V for all k in this group. Now what do I do? Then I take a function f. F is a function on this group, and I suppose that f of k1, g, k2 is equal to f of g whenever k1 and k2 are in this group. Well, that means that if I take the integral of f of g, pi of g, v. So the group is a locally compact group, and I can integrate on it. This makes perfectly good sense. If you think about what this equation means, it means that this vector is because v is unique, is a complex number times v itself. This complex number depends, of course, upon f. So, now, this set of functions is a very important set of functions. It's called the Heka algebra. I think Heka was, if you look at the introduction to Heka's works by Siegel, you'll see that it's very condescending. Nonetheless, Heka was, I think, the founder of the modern theory of automorphic forms, and not Siegel. So it's called the Heka algebra because it's very important. But what is easy to prove is that this number, this is a homomorphism. This homomorphism of the Heka algebra into C, so lambda takes the Heka algebra to C, it's a homomorphism, and such a homomorphism, it's easy to show, is associated to n complex numbers, beta 1 of p up to beta n of p, that are determined up to permutations. So since they're determined up to permutations, I think of them as the eigenvalue of a matrix that I might call A pi p, and the corresponding L function is, as you might guess. So that's what I've done is I said, well, if I start with pi, then using that last fact, namely that homomorphisms are defined by a set of n numbers, I've associated to almost every p n numbers, and I think of those as a matrix. So just rewriting the L function, L of s, now in this case associated to pi is equal to the product over p, not in capital S, of 1 over the determinant of 1 minus a of pi p over p to the s. So that's the same definition. So, whereas for Diophantine L functions, I recall, L of s was associated basically to a representation of the Galois group was a product over p, if I just work over q, 1 over the determinant of 1 minus rho of the Frobenius at p divided by p to the s. This is specializing the former general definition to q. So you see, what do we say? I said, well, there are two things. This L function I can treat. This is something associated to GLN, and although an automorphic representation remains for us a black box, GLN is not a black box. GLN is basically the set of n by n matrices apart from the exclusion of a lower dimensional subset. I can do ordinary harmonic analysis on GLN, and that means that at least as far as the elementary properties of this function are concerned, namely, as far as the analytic continuation is concerned, I can handle it. So I don't know about the zeros, that's the Riemann hypothesis, that's much harder, but the simpler analytic properties of this function I can handle. Therefore, I can handle the simpler analytic properties of this function, provided I know that this function is always one of these. And that's a harder matter than you might think at first sight. To say that this function for any rho is one of these is to say that whenever I have this collection of matrices given by rho, one for every prime p, I can find an automorphic representation such that these matrices are similar to these. And that's the basic problem. And it's a hard problem. I assure you it's a hard problem. As I said, it certainly includes, as a very special case, class field theory. But let's just see what it implies. What we want.
What is this matrix A of phi of lambda?
This matrix?
A.
This?
This one, yeah.
I do. Well, all I've said here, without going into definition, I said that whenever I have a homomorphism of the Heka algebra into C, then I can associate to that homomorphism n numbers defined up to permutation. That is clearly a statement about the structure of this algebra, right? It says this algebra is a symmetric algebra on n indeterminate algebras, and that's the standard structure theory for this algebra. It's the so-called Satake isomorphism. All right.
This is like affine the Heka algebra.
This is not an affine Heka algebra. This is the algebra of spherical functions on the group GLN. So this is the group of functions on GLN whose would satisfy this condition with regard to GLN ZP. It has a different structure than affine Heka algebras. Okay. And as I said, it's isomorphic to the algebra of symmetric functions, of symmetric polynomials and n variables. Right, yeah. All right, but let's try to see now. This is the principle. This is what we'd like to show. This would have important consequences. It would prove important conjectures if we could show that every L function of this kind was equal to one of this kind. Now, that if we can show this, that means, it almost means, for example, that any operation here it must be possible to reproduce any operation here. All right. Now the point is there are some operations here that are quite trivial that become very serious here. Let's examine two of them. See, this is let's examine base change. At the level of rho first. See, rho was associated to a representation, the Galois group of f bar over f. This is why I want it. Suppose I take a finite extension, k, or let's say E, a finite extension of f. Well then, E bar is of course equal to f bar, and so the Galois group of E bar over E I can think of as a subgroup of the Galois group of f bar over f, and I can restrict rho to rho E, which rho E is just the restriction of rho to this smaller group. And that's a trivial object. And I start off with LS rho, and I say, well, LS rho, I'm hoping at least, is associated in LS pi. Then I say, well, I can go ls rho e. This is a trivial operation because this restriction of representation to a subgroup is a trivial operation. What happens here? There must be something that I can do at this level that puts something, gives me something here that corresponds to that. And this I must be able to do. It's only reasonable to expect that I can do this without any reference to rho. Well, let's try to do it. What's the relation between, so suppose I start with one of my primes, rho p. I start with a prime of f, and then it's divisible by some prime p in E. So p is the prime of E. And so this is a prime, so I have the corresponding local field Fp. This is a complete field, and it's contained in the corresponding extension here, EP, and the degree of EP over Fp is equal to some number E, some finite number. Now this requires a little bit of knowledge of local fields and primes. I mean, so does the introduction of the Frobenius element, but not a great, it's relatively, as these things go, elementary. And in particular, it requires knowing that then the Frobenius element for the big prime, P, is equal to that at the little prime raised to this power E. So, in other words, this corresponding matrix, rho sub E of P sub P, is really just a conjugacy class, can be obtained from the original matrix by raising it to the eth power, because this element in the Galois group of E bar over E is the eth power of this element phi p. So the L function is defined entirely in terms of this, and therefore I can define the corresponding L function without representation, without really appealing to rho. I just say at every prime take the eth power. Let's see how it works here. So I want to say, what is this object? What is this object here? This object corresponds to is something else, capital pi. Capital pi clearly should be an automorphic representation of GLN, but with respect to the bigger field. You see, I started here, I said, this was a representation, the Galois group of F bar over F. It corresponded to one of these unknown objects, automorphic representation, or for the field F and of degree N. This representation is of the same degree as rho, so the degree N doesn't change, which is rho. And what changes is the field. The field passes from F to E. So all I have to tell you now, to tell you what this capital pi should be, I have to tell you what this matrix A pi sub P should be for every prime P. Here I worked over Q, but let me now come back to my Gothic letters. And this, of course, well, you've seen what it is. It's just eth power. So this is, so to speak, the defining equation for capital pi. It's not really a defining relation, but the question becomes then, does a pi with this property exist? I mean, this defines this matrix at almost all primes, capital P, and therefore it defines pi sub the local component pi p at almost all primes P. And therefore, in fact, it determines capital pi. So the real question is not whether it determines it uniquely. It does if it determines it at all. But this is a serious question. This is called the existence of a base change for pi. And the only, let me tell you what has been solved. The answer is yes, in a very simple case, if E over F is cyclic. So if the pertinent extension is a cyclic extension. Now this is a very strong constraint. Most extensions are not cyclic extensions. This is basically the content of the book by Arthur and Clausel so it requires a good thick book to prove that on the basis of some very difficult facts. So the answer is yes. But otherwise the question is completely open. Except for n equal 1. You can convince yourself that n equal 1 is an easy case with this particular statement. All right. So that's the first question in automorphic forms, one of the first basic questions that's suggested by the fact that whenever we have an LS rho, we should have an LS pi. Let me tell you now a second question that arises. So this is one of the two major problems in what might be called the internal theory of automorphic forms. That part of the theory that doesn't refer explicitly to Diophantine problems. There's no explicit reference to these rows, or hardly any explicit reference to these rows in these questions. It's a problem that arises internally, whether this capital pi exists when little pi is given. Okay, now the second question is that of the external product. See, suppose we start off now from two representations, rho 1, rho 2, of Galois of f bar over f. Then another trivial operation is to build the tensor product. At the level of, I should perhaps have stressed that this is an equality as conjugacy classes, not an equality of matrices. Just I mean that matrices have the same eigenvalues. So that would mean that this would be rho of phi sub p would be rho of 1 of phi sub p tensor rho 2 of phi sub p. That means that if rho 1 was associated to the numbers alpha 1 of p, alpha n of p, or m of p, say, if m was the degree of rho, and rho 2 was associated to beta 1 of p, beta n of p, where n is the degree of rho 2, then rho of phi of p would be the matrix whose eigenvalues are alpha I of p, beta j of p. So these are to be thought of as the matrices, the elements along the diagonal, so the eigenvalues, and then we have zeros off the diagonal. On the other hand, the corresponding problem for automorphic forms would be, I would have an automorphic form pi 1 on GLM and pi 2 on GLN. Then for almost all places. And here I could work over. I mean, here the problem is the series over Q is over any other field. Then I would have pi 1 at every p. I would have a pi 1 p, these would be numbers alpha 1 up to p, alpha mp. And I'd have a of pi 2 of p, which would be beta 1 of p up to beta n of p, which are determined by the representation theory. And what I'm looking at is a pi, which is an automorphic representation of GLM times n, the degrees multiply, such that a of pi of p, the eigenvalues associated to pi of p were just obtained by taking the products of those associated to pi 1 with those associated to pi 2. And here, so the second question is, given pi 1 and pi 2, does pi exist? Now, this is a question not about representations as such, but about automorphic representations, which I'll come back. So, I mean, to build such a representation, pi is easy enough, but it has to be an automorphic. So that's the constraint. And so pi we would call the external tensor product of these two objects, pi 1 and pi 2. And this is really a more serious, I mean, for the previous problem there were some serious results, the results for a cyclic extension. Here there are no serious results whatsoever. So anything you might be able to do would be appreciated. And these, I think, are the two, I've just given you the two central problems of the internal theory of automorphic forms, namely the existence of a base change for an arbitrary finite extension and the existence of external products. For n equal 1, by the way, the existence is no problem at all. For n, if n or m is equal to 1, the existence is assured and easily. Okay. Now, historically, these problems I formulated in that way because I think that the need to solve them is manifest when one considers the relation with Diophantine equations. And it's clearly not going to have any serious theory that connects automorphic L function with Diophantine L function until you can solve these two problems. Now, historically, they arose in a broader context. Historically, these two problems arose. I mean, this is not entirely true, but historically, in a certain sense, these two general problems, arose inside the theory of automorphic forms. This is an overstatement. I mean, nothing is that simple. And this general problem one can call functoriality in the L group, and I'd like to explain that. One of the advantages about this, the more general problem, is that one can solve it in some cases, more cases. So let me give you some examples of L groups for classical groups. Let me tell you what I mean. In other words, I'm going to move away from GLN and consider an arbitrary reductive group over a number field. So For example, I can consider G to be, I can take G to be the symplectic group in 2n variables over the field, just the ordinary symplectic group. And then there's associated to G, this is the first example, a complex group which is called the L group, and that I can think of as the special orthogonal group in 2n plus 1 variables, but this is just an ordinary complex group. And if I want, I can take the product with the Galois group. A finite extension or an infinite extension, it doesn't matter. This is an unimportant feature here. I point out that if I had taken not the symplectic group, but the its adjoint group, if I'd killed the center, then this would be the spin group. And the spin group is a fairly complicated group. Well, so if G were the special orthogonal group itself, G were the special orthogonal group in 2n plus 1 variables, then the L group is again a complex group, but it's a symplectic group in complex group. And I'll give you one more example. I'll put it up here. And I can take a product with a Galois group. And one more example would be to take G to be orthogonal group, special orthogonal group in 2n variables. But the difference between the special orthogonal group in 2n variables and an odd number of variables and an even number of variables is that this, so to speak, has many, many more outer forms. So built into this, I won't go into it, it's related to the determinant of the associated quadratic form, is a quadratic extension. E is a quadratic extension. It could be trivial. E is either F or is a quadratic extension. And the L group is again the special orthogonal group in 2n variables over C, but provided now really with an action of this, with a non-trivial in general action of this Galois group of E over F, and I can think of that as the Galois group of F of K over F, or K could be any finite extension that contains E, or F bar. So that's only to stress that sometimes this second factor plays a role because it acts on the first. Now, what's the pertinence of this second factor, of this L group? For GLN, by the way, the L group is GLNC. The pertinence is the following. Whenever I have pi, which is now an automorphic representation of G, of the group G over AF, and this is a harder object to deal with than an automorphic representation of GLN because there's no underlying linear space, then I can associate, so pi is associated to the local representations, and now associated to pi p is a conjugacy class in this complex group GL. And I observed that this projects to the Galois group, and this conjugacy class projects to the Frobenius. Once again, I'm excluding a finite number of primes. So the same kind of general and not very difficult theorem that we use for GLN, namely the structure of the Heka algebra, allows us to associate to this pi and almost every place p a conjugacy class, but in this group. Now, and here's the question that arises. Suppose I have now the general question that arose historically, and of which the two basic questions are special cases, is the following. Suppose I have two groups, G and G prime. They can be quite different, and in particular there may not be a homomorphism between them. And suppose I have a map from GL, this is the L group, to GL prime. This is a homomorphism, a complex analytic homomorphism of two groups, two complex groups. And suppose over here I start with pi. That means I start with this collection A pi p. One for every prime, which is a conjugacy class. So this could say be a map phi. And I suppose it, to make sure that this condition is respected, I suppose that this homomorphism is compatible with the projection to the Galois group. And suppose I start with this. Well, then I can apply phi to it, because this is a homomorphism at this level, and I get an A prime of p. Now, this is a funny thing to do. If you look at what it means, it's a very funny thing to do. And I can ask, is there a pi prime over on this side associated to G prime from which these conjugacy classes in this group come? So that's the general question. So the principle of functoriality, so in the L group would says yes. The answer is always yes. That's something to be proven. This in itself has very strong consequences. It implies immediately outstanding conjectures like Darton conjecture. You have to think about this principle for a minute, and you have to ask yourself, for example, just how complicated is it even in the case where I take G to be the trivial group? I can take G to be the trivial group, and there's a very powerful principle even in that case in G prime be GLN. Because this, even if G is the trivial group, GL is not the trivial group, it's the Galois group. And so I have homomorphism from the Galois group. So whenever I'm asking in particular, whenever I have a homomorphism from the Galois group into GL prime that respects this projection, there should be an automorphic representation. That means I want a lot of automorphic representation right off the bat. So in particular, Artin's conjecture for Artin L functions follow from it. Now, the advantage now is that whereas, first of all, this was the question that arose first, and the advantage of a broad question over two questions is that one can attack special aspects of a broader question and hope there's more chance that the broad question has an exposed flank than that the narrow question has an exposed flank. But I want to just indicate before I go on what the source of this general question was. Namely, you see that I have, what I've just said is that if I have pi, I have almost the ingredients for building an L function. Namely, I have at every place P an object, right? So I should say, let me build an L function associated to pi, namely the product over all P, I may be true to find finite number, 1 over, let's build it just the way I built the other thing, 1 minus A of pi P over norm P to the S. And then you'll notice that I've done something that I shouldn't have done, namely I've taken a group element and put the determinant here, so this doesn't make any sense. To make sense of this, I need something here that makes this a matrix. So I take a representation R of GL. So R is a representation of GL, an ordinary complex representation of this finite dimensional complex analytic group GL. So I have associated to this little object pi and any R an L function. So I have, and there was a time, not even within living memory for many of you, where people really were looking around for L functions. They thought there should be a lot more. They didn't know quite why, but that was the idea. And this class was discovered, and it was discovered in such a way that one could see, at least for certain groups and certain representations pi, that indeed this was a good L function. first only defined in a half plane, could be analytically continued to the whole plane. So that it was a good L function regardless of anything, regardless of functoriality. But the point of functoriality is it says that, look, you're wasting your time on all these L functions, because if you give me pi for G and R, that means you give me GL into GL and C, where this is the degree of R, n is equal to the degree of R. This product, if I take this product with the Galois group, F bar over F, is the L group for GLN. So this is the L group for GLN. Then this L of S pi R is, provided the principle of functoriality is satisfied and pi is associated to a pi prime, nothing but the L function I originally defined at the beginning of the lecture for LS pi prime. So what it says is that the person who introduced these L functions was in some sense wasting his time, because if you could only establish the principle of functoriality, they would all be equal to these ones that you can already handle, that you can handle by elementary Fourier analysis. So playing around with various methods for establishing the analytic continuation of these L functions is not an appropriate activity. One should really show the existence of pi prime, and in the analytic continuation all other analytic properties presumably follow easily. Okay, but now comes the question as whether or not in any cases at all one can prove the existence of pi prime starting from pi and a homomorphism between two L groups. And I think this would be what I want to do is discuss next time. Certainly we do not have any method that will get that in a great deal of generality. But there are methods available that will give you serious methods, only partially developed, that give you, I think, serious results, and I want to discuss these methods next time. In particular, I think what I will discuss is to some extent what is contained in the book. I'll give you an idea of what is contained in the book of Rogowski on U3. Rogowski discusses these problems for, I mean, not all problems, but some particular cases of functoriality for the group U3, and it's interesting to see what that means. And so I think I'll spend the next lecture talking about that, and then on Tuesday I think I'll go back and tell you what we know at the moment about the connection with Diophantine equations. Okay, thank you.